So in the last class we completed with the adder circuit. No, adder is full adder, half adder, and full adder. We completed, I think so. So next we'll start with last class we completed this adders. No, half adder, full adder. Okay, half adder and full adder we completed. Today we'll start about this. Yes, new one. Yeah, K map. Okay, only K map we completed. Okay, okay. Okay, so that means today we need to start the combinational circuits. Okay, today we need to start the combinational circuits. Okay, so what are these combinational circuits? We'll see. MFC completed. Okay, combinational circuit. One second. Okay, combinational circuit. If you see combinational circuit, so in the digital system you have like so basically if you see the digital system, so basically in the digital system. If we see the digital system, so digital system you have first we already seen that representation of this number system. Okay, number system and conversions we already seen. Okay, so representation of information in digital form. Okay, one second. Yeah. So yeah. First representation of information in digital form. In digital form. So digital form and digital form like binary codes, number system and conversions we already seen. Okay, binary codes, number system. Okay, we already seen. One second. Yes. Okay. So binary codes. Okay, and we already seen like a 8421 code, a gray code. We already seen. Okay, and next we seen about Boolean algebra. One second. Happening. This. Yeah. Boolean algebra we already seen. Boolean algebra, and logic optimization we already seen. Optimization. Okay, logic optimization. Example like you have y equal to dash t plus ab dash. Okay, and next you have combinational circuits. Combinational circuits. Combinational circuits. Combinational circuits. Okay, combinational circuits are nothing but multiplexers. Okay, adders, subtractors. Okay, these are the combination circuits. And next you have sequential circuits. Sequential circuits. Sequential circuits. Okay, sequential circuits like latches, flip-flops, counters, and registers. Okay, and next system design. System design. System design. You have processor. Okay, so basically this is a digital system. Basically, we'll study about this these things in the digital system. Okay, one second. Yes, am I audible? Give a response. Hello. Yes. One second. What happening? Yeah. Okay. Yes. So here, this is about the digital system. Next, we will see the abstraction level in digital circuits. Okay. So what is the abstraction level in digital circuit? Abstraction. So abstraction level in digital circuits. Level in digital circuits. Digital circuits. So basically, like, so first you have like basic device level. So basically, device level will be like you have NMOS or PMOS. Okay, so NMOS and PMOS. So this is device level. Let us take this is the CO2 layer, and this is gate, and this one is drain and source. Okay, so this is the drain and the source. You have gate, and this is a N plus, and this one is N plus and P substrate. Okay, P substrate. Next you have, this is nothing but we call as a device device level, and next you have CMOS circuit level. This is nothing but CMOS circuit. So this is VDD and ground, VDD and ground. Okay, so this is circuit level. Okay, and next you have gate level. Gate level means sometimes some inputs are there, and this is gate. Okay, and next you have module level. uh, like you can use adder circuits or multiplexers or counters. Okay, these are nothing but modules. Okay, module level, and next so this is a module, and next you have processor level. So this is processor level. So you have inside there will be chips, the ICs are there. This is system level or processor level. Okay, so there is a bottom to top approach. Okay, so this is nothing but bottom to top approach, and top to bottom approach. Okay, so like so that means bottom to top means you need to come for device level, circuit level, gate level, module level. So device level means you can use a device like NMOS or PMOS. Okay, and next you can use circuit level means you can use CMOS. With the help of devices, you will use CMOS. Gate level means you can use like AND gate or gate, NOT gate, okay, NAND gate. These gates you can use. And module level means what? Module level means we can use adder circuits, adder or a comparator, multiplexer. These you can use. And system level means you can use a processor. You can use processor. Okay. So this is bottom up approach. Top down approach means what? So here you need to come with system. System is made with modules. Modules are made with gates. Gates are made with circuits. Circuits are made with devices. Okay. So basically highest level. If you take highest level, so highest level is CPU. highest level is CPU, and lowest level is like resistor or transistors, capacitors, and inductors. These are the lowest level. Okay, so this is the abstraction level. Okay, this is basic abstraction level. Okay, so basically, if you see this combinational versus sequential. Okay, what is the combinational circuits versus sequential circuits? Okay, combinational versus sequential circuits. Okay, so what are these combination versus sequential circuits? Okay, so combination versus sequential circuits. Here I'm writing combinational. Next sequential. So combinational versus sequential. If you see, basically for the combinational, the output is depends on only on the input. Okay, so output is depends on only present input. Okay, present input. So that means I can say that output is what function of present input. Present input. Okay, output is function of present input. And here output depends on what? Depends on present input as well as past output. Past output. Okay, so output is a function of what? Output is function of present input as well as past output. Okay, past output. Okay, and here this is the block diagram. So this is the combinational circuit. And whereas sequential circuit, so we have a combinational circuit, some set of inputs. Okay, combinational circuit, some set of inputs, and this will be feedback. Okay, this will be feedback through this you are giving through the memory, and here you are getting like this. Okay, there will be feedback. Okay, so here no feedback. Here there will be no feedback and no memory. No feedback and no memory. Here possibility of memory and feedback. Possibility of feedback and memory. Possibility of feedback and memory. Okay, example, if you see like half adder, full adder. Okay, and next mux, demux. Okay, so mux, demux, and next you have mm, comparator. Okay, comparator, comparator, code converter, code converter. These all are nothing but combination circuits. Okay, sequential circuits are nothing but latches, flip flops. Okay, and counters and registers. These are the sequential circuits. Okay, so this is about combinational versus sequential circuits. Okay, so what are the steps to design? So some more differences if you see like memory. So that means combination doesn't have the memory and sequential have the memory. Okay, feedback, combination doesn't have the feedback and sequential have the feedback. Okay, processing speed, if it is there, it is fast. It is fast, and this one is slow. Processing speed. Okay, so why? Because here this should be feedback. No, this should get feedback. Okay, processing speed, it is fast and it is slow. Okay, and memory, it is there and it is not there, it is there. Clock. So clock, if you see, clock is independent of clock. There is no clock independent of clock. Here there is a clock. It depends on the clock. Okay. So this is the basic difference between combinational and sequential circuits. Okay. Next, if you see how to design the combinational circuits. Okay, how to design the combinational circuits, design steps, design procedure for combinational circuits. Design procedure for combinational circuits. So what are the design procedure for combinational circuit? First, step one. Step one. So what is step one? From the specification of the circuit, identify the number of inputs and outputs. Okay. From the specification of circuit, identify the number of inputs and outputs. Okay, inputs and outputs. Okay, and step two, derive the truth table that defines the relationship between input and output. Okay, derive the truth table that defines the relationship between input and output. Okay, obtain the simplified Boolean function for each of the output using K-map. Step 3. What is step 3? Obtain the simplified Boolean equation. Simplified Boolean equation by using inputs and for each output. Simplified Boolean equation for each output using K-map. Okay, and next step 4. Draw the logic circuit. Okay, draw the circuit using logic gates. Draw the circuit using logic gates. Okay, draw the circuit using logic gates. Okay, so this is the basic design procedure for combinational circuits. Okay, is it fine? Any doubt in this? Yes. Shall I move forward? Okay. Yes. Okay. So next, if you see, so I want to design. So here I want to design a circuit. So just with the examples related to this combinational circuit. Okay. So combinational circuit designing examples. Let us take some examples. Okay. Let us take some examples. Okay. Uh, the minimal function. That can be the minimal function that can detect divisible by 3, divisible by 3, and divisible by 2 will take. Okay, divisible by 3 you do as task. Okay, with 8421 BCD, 8421 BCD, those are nothing but D8, D4, D2, and D1. Okay, is given by. Okay, so here what he is asking, that means here you need to design the combinational circuit such a way that should be divisible by what? 3. That will be divisible by 3. So let us take this is BCD. So what is the range of BCD? BCD range is from 0 to 9 only. Okay, so that means D8, D4, D2, and D1. Okay, first identify the number of inputs and number of outputs. How many number of inputs are there? So inputs are 4 and outputs are 1. Okay. So let us take first. So after identifying, you need to draw the truth table. Okay. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0 double 1 0 0 triple 1 1 0 0 0 1 0 0 1. Okay, from 1 0 1 0 to 1 1 1 1, those are not defined. Okay, 1 1 1 1, those are not defined. That is defined only at the range of the BCD is only from 0 to 9 only. Okay, in the problem he given, this is nothing but BCD. Okay, and now first you understand the problem that should detect divisible by 2. So that means 0 is divisible by 2. No, so this output is 1. 1 is not divisible by 2. Output is 0. 2 is divisible by 2, and 3 is not divisible, and 4 is divisible, 5 is not divisible, okay, 6 is divisible. So whatever this divisible by 2, you need to write the output as 1. Okay, if it is not divisible, the output as 0. Okay, 8 is divisible, 9 is not divisible, and this from here to here, this is don't care. Why? Because BCD, those are not defined. Okay, so if you write the SOP expression, summation of m of, this is nothing but 0, 2, 4, 8, that's it, 8 plus summation of don't cares of 10 to 15. 10 to 15. Okay. So next you need to draw the K map for this expression. K map for this expression. So if I am drawing the K map, so what are the inputs? D8, D4, D2, D1. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 1 2 3, next 4 5 6 7 8 9 10 11, next 12 13 14 and 15. Okay, you need to write the min terms, whatever the min terms are: 0 2 4 6 8 10 to 15 are nothing but undefined or don't cares. Okay, so don't cares K map we already seen. Depending on the possibility, you can consider that this don't cares as either 0 or 1. Here I'm considering this don't care as 1. Okay, this don't cares as 0. Okay, so if you consider this don't cares as 1, I will get one octet. I'll get one octet. Anyway, octet will eliminate at how many variables? Octet will eliminate 3 variables. Okay. So here, which is common? That means 0 is common. 0 is common means I will get y equal to what? Y equal to d1 bar. Y equal to d1 bar. So that means how you will design? That means this is one inverter d1 and y equal to what? Which one inverter? d1 bar. Okay, d1 bar. Okay, so your task is, this task you need to do and just share in the group. So you need to design to detect divisible by 3, divisible by 3. Okay, is it fine? This one is fine. Give response. Any doubt in this? Yes. Yeah. Okay. Okay, next you see. So next so this is one type of problem. Next, suppose combinational circuit, they given in terms of gates. Okay, how to do? Okay, they given in terms of gates how to do. Okay, so we'll see. Suppose like they given in terms of gates, in terms of gates, how to design this combinational circuit. Okay, so they given like this. Okay, yeah. So see here. So let us take this is AND gate, and next this is NAND gate, NAND gate, and this one is given to one NOR gate. Okay, NOR gate, and here one XOR gate, XOR gate. and this is let us take A, B, and C is coming like this. C is coming. Okay, C is coming, and here D is let's take this is XOR gate, and this is connected with a bubble, with a bubble. Okay, and here uh, this input is connected like this. Okay, so here how to realize this circuit. Okay, so here you know that this is nothing but AB. Okay, let us consider AB equal to what? X. Okay, here you what you are getting? AB bar. AB bar equal to I can consider as X bar. So here if you see, this is X plus X bar, X plus X bar. So in Boolean algebra we already seen. So that means R la A plus AR A bar equal to what? 1. Okay. So XR X1 X bar equal to what? 1. Okay. Here you are getting 1. 1 and C. Okay. So 1 and C means what? C you are getting C XR of 1. So we already seen the properties of XR. A XR 1 equal to what? A bar, no? A XR 1 equal to A bar. So you know that A bar B plus AB bar. In place of B, 1 is there. So that is A bar and 1 plus A into 1 bar. Okay, so this is A bar and 1 plus A and 0. So A bar plus 0. So this is equal to A bar you are getting. Okay, so this is nothing but you can write as C bar. Okay, and next D, one input is D, another input is D bar. Another input is D bar. So this is nothing but if you consider D XR D bar. Okay, we know that A XR B equal to what? A XR B equal to A bar B plus AB bar. So this is equal to what? D D bar D bar plus D into D bar whole bar. So this is D bar plus D bar. Complement of complement is true form. From AND law, this is I can write 1 D bar. This is D. So D bar plus D equal to what? 1. So this is nothing but 1 you are getting. Okay. And next C bar. This is X nor. This is X nor. Okay. So X nor means what? This is C bar X nor XR1 whole bar. So this is nothing but C bar X nor of 1. Okay. So we know that A X nor B equal to what? A bar B bar plus A. A bar B bar plus AB. So this you can write as, so in place of A you have C bar, in place of B you have 1. So C bar whole bar and 1 bar plus C bar C bar and 1. Okay. This is C and 0 plus C bar and 1. So this is this is 0 plus C bar. Here you are getting C bar. So this is nothing but C bar. This is nothing but C bar. So like this you will get. You are getting the output expression y equal to C bar. Okay. Y equal to C bar. So like this you need to realize this function. Yes. Any doubts in this? Your response? Yes. Fine. No. Yes. Okay. So next type of problem, if you see, suppose redundancy of gates. Redundant gates means suppose like they given mm, redundant gates. Okay, how to realize this redundant gates? We'll see. Redundant gates. So redundant gates are nothing but suppose the given three gates are there and gates. This is Y. Okay. This is A B bar C, A bar B bar C, A, B, C bar. Okay. So this is the gate 1, gate 2, gate 3, and gate 4. Okay. So this is NAND gate. So if you write this is A B bar C whole bar. So if you apply De Morgan's law, what you are getting? A bar plus B bar whole bar plus C bar. Okay. So this is if you write A bar plus B plus C bar. Okay. Next, this one if you write, so this is A bar, B bar, C whole bar. So this if you write A plus B plus C bar. Complement of complement is true form, no? So if you apply De Morgan's law, you are getting this. And this is A, B, C bar. A, B, C bar whole bar. So this is A bar plus, one second. I'll check whether recording is happening or not. Yes. Okay. Yeah. So, yes. So this one, if you see, this is nothing but A, A, B, A bar, B bar, C. Okay. So now if you see, that means here if you see A bar, so A bar, if you see A bar, A bar is repeated in this gate. Okay. Uh, B if you see, B if you see, B is repeated in this gate. And C bar, if you see, C bar is repeated in this gate. Okay. So that means this is nothing but I can say that this is redundant gate. Okay. If you observe here, A is not repeated in any of the gate. Okay. I think B is repeated. Okay. C bar is repeated, but A is not repeated. So this gate should be present in my design. Okay. Similarly, if you see this one, C is not repeated in any of the gate. So this design should be connected. So what is the redundant gate? So what is the redundant gate in the given circuit is redundant gate. Redundant gate. Redundant gate is what? That is gate one. Redundant gate is gate one. Okay. Like this, you need to find out the redundant gate. Okay. Okay. One second. Yeah. Yeah. Is it fine? Do you understood this redundant gate? Any doubt in this? Just give response so that I will move forward. Redundant gate. Hello. Yes. Okay. Next you see. So two more examples we'll see and we'll wind up. So next example, if you see, so he is asking to find out the redundant gate. Okay. So he is asking to find out the redundant gate. Let us take. So this is X, Y bar, Z. This is X bar, Y bar, Z, X bar, Y, Z. Okay. So this is given to one OR gate, one OR gate, OR gate. So what is the redundant gate? 1, 2, 3, and next 4. So this is what x y bar z whole bar. Okay, this if you apply De Morgan's law, x bar plus y plus z bar, and this one is x bar y bar z whole bar. So if you write in De Morgan's law and if you apply x plus y plus z bar, you will get. So this is x bar y z whole bar. So x plus y plus y bar plus z bar you will get. Okay. Now you find out the redundant gate. So if you see X bar is nowhere repeated in any of the gate. So this gate should be present. And this one, if you see, X means X is repeated in this. Okay. Y means what? Y is repeated in this. Okay. Z bar is repeated in this. Z bar is repeated in this. So that means this is a redundant gate. Okay. If you see this one, Y bar is not repeated in any of the gate. So this should be present in my design. So the redundant gate is what? Gate 2. Gate 2 is my redundant gate. So like this we need to see. Okay. One more example, like let us take so these inputs are A, B bar, C, A, B, C. Okay, A bar, B bar, C bar. Okay. So this is given to OR gate. This is given to OR gate. So what is the redundant gate? So four gates are there. So what is this? A plus B bar plus C, A plus B plus C, and A bar or B bar or C bar. And next, so now you see. So A is repeated here, B bar is repeated here, and C is repeated in this gate. So this is a redundant gate. Okay. And next, if you see B, B is nowhere repeated. This should be present in my gate. And C bar is nowhere repeated. This should be present in my gate. So what is my redundant? This is also redundant gate. Okay. So what is the redundant gate? Redundant gate is gate one. Gate one is my redundant gate. Okay. So this is about the combinational circuits. So today we discussed about what is digital system. Okay. What are there in the digital system? Okay. And next, basically first we learn about this number systems, conversions, binary codes. Okay, like ASCII codes, XS3 codes, the gray codes, weighted codes, non-weighted codes, those we study. And we study about Boolean algebra and logic optimization. We already seen that how to realize by using logic expression by using only NAND gates and NOR gates, logic gates we see. Okay, and next combinational circuits like adder, subtractor, sequential circuits like flip-flop counters and registers, and system design. Okay, so this is level of abstraction. How the level of abstraction will be there. One is bottom to top and top to bottom. Bottom to top means first is device level, next circuit level like CMOS, next gate level like AND gate and NOR gate, and next module level like adder, comparator, multiplexer, and next processor. Okay. Top down approach means first it will come with processor, and next adder separate module level, gate level. Gates are made with circuit level, circuits are made with devices. Okay. Basically this combination and sequential, the output depends only on the present input. Output depends on the present input as well as past outputs. It will be feedback. Okay, this is fast and this is slow, and this doesn't have the clock. This is having the clock, and doesn't have the memory. This is having the memory. And example, half adder, full adder, mux, demux, and this is we already seen like latches, flip flops, counters, registers. Okay, so these are the design steps, how to design this design steps for. First, you need to find out the number of inputs and outputs and the functionality of the circuit specification. Next, you need to draw the truth table, and you need to get the relationship between input and output. So obtain the simplified Boolean expression by using KMF. By using Boolean expression, you need to draw the circuit by using logic gates. Okay. So we already seen that divisible by 2. Divisible by 3, you need to, this is one example of designing a combination circuit. Divisible by 3 is your task. Okay. So this is like gates they given, how to design. Okay. So you need to realize each and every output of the gate, and at last you need to get the output. Okay. And next, this is redundant gate. So redundant gate means you need to write the expression for this, and whatever the variables are repeating in another gate, those are nothing but redundant gates. Okay. So we see in three problems related to the redundant gate. Okay. Yes. One second. Yes.